Let's welcome Janmajaya Mall, developer from Ethereum Foundation, with the topic Boost Your ZKP Using Aggregation workshop. Please give him a round of applause, guys.
Hello everyone, I'm Janmajaya. I work at Privacy and Scaling Exploration Group at Ethereum Foundation. And today I'll be talking about magical aggregation. That is, how do you take a bunch of proofs and then aggregate them into a single proof and submit it on chain. So, right now, how do you generate a Groth 16 or a Plonk proof using Snark.js? So first, you perform a setup ceremony, and then you run the command Snark.js setup, and then prove, and then verify, and then optionally, you can generate already called data so that you can submit it on chain for verification. But when you actually submit a proof on chain for verification, what does it cost? So basically, the first cost is the call data cost, and the second cost is the execution cost. So for Groth 16, for one proof, the execution cost is 210,000 gas units. The call data cost, if you have zero public inputs, it's 128 bytes. For Plonk, the execution cost is around 300,000 units. And the call data cost, again for zero public inputs, is 400 bytes. And needless to say, if you want to verify 50 Groth 16 proofs or 50 Plonk proofs on chain, everything would be times 50. So the gas cost becomes 10.6 million and the call data cost becomes 6400 bytes. But what if I told you that you don't have to live in that world anymore? What if you could verify 50 Plonk proofs at the cost of 1? And we can do that using aggregation. So what is proof aggregation? Basically, you can take a bunch of proofs and then aggregate them into a single proof, and that is what we call aggregation. And how do you do it? Right now, you can use a tool called Maze, which is a CLI tool to aggregate a bunch of Plonk proofs into a single proof. And why should you use it? So when you actually aggregate a bunch of Plonk proofs into a single proof, the call data cost is always constant. So it doesn't matter how many proofs you aggregate, 30, 40, 50, 100, the call data cost would always remain 4320 bytes. And the same goes for the execution cost. So execution cost would also be constant, and that would be approximately around 600,000. So let's try it out. Yeah, so to aggregate a bunch of Plonk proofs, you first need a Plonk circuit. You first need a circuit for which you will be aggregating the proofs, and for which you will be building the aggregation circuit using Maze. So we'll be using Snark.js, a focused Snark.js, to generate Plonk proofs, and then we'll use Maze to actually build an aggregation circuit for those Plonk proofs. So I would first, wait, where did it go? Yeah. As you can see over here, I've got a circum circuit. And I've already generated the necessary files for the circum circuits. As you can see over here, I've got the WASM file for the circuit and the rest of the files like R1CS, SIM and ZK key. Over here, we have generated ZK key for the Plonk proof. ZK key is the Plonk proving key, and we have generated using Snark.js. First, you will have to install a focused Snark.js, which actually introduces this new command. I think it's visible, right? Yeah. As you can see over here, there is a new command added called Plonk setup Maze. Wait, you're not able to see it. Now is everyone able to see it? Plonk setup Maze, right? So what this does is it actually helps you it helps you generate the necessary files for building aggregation circuit using Maze. So you'll be using this specific command to output files that you will actually use in Maze CLI tool. So let's just use this command. Long setup Maze. And it needs an input.json file which would contain array of inputs for which you will generate the proof, circuit.wasm file which we actually generate using circuit compiler, circuit.zk file which is the Plonk proving key which we previously which you can generate using Plonk setup. Plonk setup right here, and then this command would output proofs.json, public signals.json, and the verification key. So we would need these three files for Maze. Yeah, and circuit.zk file. Yeah, so we'll. I'm sorry for this thing, but we should. I'm just a bit uncomfortable typing with one hand, so I'm sorry for that. So you would notice that it's okay. So you will notice that it has generated three additional files over here, proofs.json, which contains the proofs on these inputs. So we've got two inputs and we've got two proofs over here. Public signals files and the verification key. Now we'll use these three files to actually build an aggregation circuit for proving, for aggregating these proofs. So, and for that we'll use Maze. So let's just call Maze and help. So it's okay. So you can see over here that you've got. Is it visible? Yeah. You've got a bunch of commands over here. The first command is mock setup. So what mock setup does is that it will take the proofs, build an aggregation circuit, and run a mock prover on it. So what is a mock prover? Mock prover is sort of simulating the proving. Sort of simulating what a prover does, but it does it in a lesser time. It's like if the proof generation takes 50 minutes, it will do it in 5 minutes for you and sort of verify that everything is correct. You've got generate EVM verifier, which generates the EVM verifier for the aggregation circuit that you're building. You've got verify proof, you can verify the generated proof. You've got EVM verify proof. What it does is that it will simulate EVM verification of the aggregated proof. So for the demo purposes, I'll be sticking to mock setup because generating a proof for aggregation circuit is pretty computationally expensive, and it might take 20-30 minutes to actually generate a single proof. So I'll just stick to mock prover for now, but you can sort of use the same command for the rest of the commands that you can see over here. So let's see what are the input files that mock setup needs. Thanks. So as I said before, for building an aggregation circuit, you need the verification key, proofs, and public signals. So I'll simply supply those files over here. It's almost done. So it first reads the file, builds the aggregation circuit for two proofs, and right now it is running mock prover on the aggregation circuit. So it might take 20 seconds or 10 seconds to actually show you whether everything went correctly or not. And yeah, let's just wait for it. Okay, yeah, there you go. So it was a success. It actually used, so what is K? K is number of rows. So 2 to the power 21 rows were required for building this aggregation circuit. And it took 26 seconds to actually run the mock prover on top of it. So this is how you build an aggregation circuit using Maze and of proofs generated using Snark.js. Okay, so all this is good. You are able to generate proofs and build an aggregation circuit. But like, how does it work? So basically, a Plonk proof, a single Plonk proof, consists of two parts. The first part is the cheap part, and that is performing computations to actually do the final part, that is the expensive part. And the expensive part is the pairing check of the values computed in the cheap part. So in the aggregation circuit, the trick is that you verify the cheap part within the circuit and then accumulate within the circuit the expensive part, that is the values for the pairing check, into a final accumulator. And then you actually expose the final accumulator as the public input to the proof of the aggregation circuit. Now what the verifier does is that it will verify the proof of the aggregation circuit. That means the cheap part of all the Plonk proof is valid, and then it will perform a single pairing check on the final accumulator. So we've actually reduced the expensive part into a final single expensive part, which is outside the proof, which happens alongside the proof verification. And that's it. So the verifier now is satisfied that all the proofs that were aggregated are valid. So we were able to sort of aggregate like 50 proofs. You can even extend it to 70 proofs or 100 proofs. But we are actually trading something off over here. The point is that aggregating proofs is very expensive. So as you can see over here, for 25 proofs, it takes 27 minutes on a pretty beefy machine with a peak RAM of 107 GB to build an aggregation circuit. For 50 proofs, it takes an hour. So it's still an expensive thing. And yeah, that's it. If you want to check out Maze, you can actually scan this QR code or visit the GitHub profile. And if you want to actually contact me, this is my Twitter account, and you can call me anytime. Any questions?
Thank you. Any questions?
Hello. Does Maze get used in production?
So basically, the circuits, the aggregation circuit is unaudited, so we wouldn't recommend you to actually use it in production, but you can actually try it, and we would love you to try it out, because that would actually tell us whether it is useful for people or not.
And are there any use cases, like particular use cases that you envisage it being really suitable for?
Yeah, so basically the initial concept behind Maze was that you've got a lot of circum circuits, you've got a lot of circum developers, right? So they write circuits in circum, and then they've got, and the limitation in that case is that they can only sort of prove one proof at once. So how about like enable them to actually build aggregation circuit automatically from circum files? As you can see over here, we were using Snark.js, right? So we were trying to actually bridge the gap between Snark.js and building aggregation circuit, and Maze was one of the ways to do it. But yeah, there might be better ways, and if there are new ideas about it, do let us know.
Cheers, thank you.
Sorry, yeah.
Hello everyone, I'm Thành from Turkish Network. I am very interested in your topic, and I see that your idea is similar to something that the output of your proof is fixed and similar to a hash function, and you use it to keep to save computation. And I have a question that is there any theories proof that does not affect the security level a bit?
Okay.
Yeah.
So if I get your question correctly, you're asking that whether it is like what's the are you missing any security when you are aggregating proofs? So for that, so the concept that Maze uses it is based upon something called incrementally verifiable proof. Yeah, so the concept is that there's a paper out there on this, not on Maze, but the concept that we've used, and if you want I can share the paper afterwards. But the concept is that you can actually accumulate the expensive part of different schemes into a final accumulator, and if you can verify it outside the proof. So you verify the accumulation within the circuits, and then you perform the expensive part of the accumulation outside. So you reduce the expensive part that you perform for n proofs into a single one. So that's how it works, and it maintains security. And this thing you can actually check out the paper for that. I would definitely send you the link. But like the circuits for Maze aren't audited as of yet. So I'm not sure. Like we aren't sure whether this is completely secure or not. But the scheme entirely in the entire sense is secure.
Is Maze similar to something like a recursive snark?
Yeah, so I'm not sure what's the theoretical difference between aggregation and recursion, but the concept is that it is aggregation and recursion is sort of the same thing, because once you verify the aggregation proof, you recursively verify each and every proof which was aggregated to the proof, right? So for example, you had 5 proofs for which you actually generated an aggregated proof, right? Once you verify that proof, you're recursively verifying all the 5 proofs, right? So yeah, that's how I think about it, and that's how I imagine it, but I'm not sure about the theoretical difference between recursion and aggregation.
Any other questions? I think that's pretty much it. Thank you, Janmajaya. And yeah, let's give him a round of applause. He did really well, right? Thank you.